Welcome back, and to the topic this week, which is a continuation of what we had last week about the particle Hall formalism. And what we are going to do today is to discuss in more detail with examples how we can, in a very efficient way, calculate expectation values of different types of operators when we have a many-body state which involves many particle states. And one of the motivations for introducing this new vacuum and this new reference state is simply the fact that when we are dealing with many particles, the equations which we end up with, all the possible contractions, is something which becomes pretty cumbersome to deal with. So we are looking after a more compact way of calculating different expectation values and transition probabilities, etc. And then with this one, we have then the basic elements which we're going to need for the rest of the semester. So this will allow us to compactify most of the formalism which we need in order to deal with more complicated systems. So what I wanted to give you first, and these notes, parts of the notes you will find in the slides here, but you will find most of the more relevant ones in the on the whiteboard notes. So let me switch to the whiteboard here, and then we will mainly stay with that one for the rest of the day. So let me quickly change here. So what we had was a redefinition from last week of the creation and annihilation operators with respect to a new vacuum state. So let me just quickly bring up some of the definitions which we put forward last week. So one of the things we did was to introduce new operators. So the first 5 to 10 minutes are mainly going to be a reminder of what we did last week. And we defined a new vacuum state. And these operators are operators which we later today are going to change back to the original ones. And what we had was an A alpha dagger, A alpha. Yeah, hi guys, we needed to change room because they have this course running. So we will sit here tomorrow as well. And I think we all fit in here, I think. So I was just starting with a repetition from last week. And maybe we can just close the door as well. Yeah. Because then we don't get disturbed here. So F stands for the Fermi level. And then we had the annihilation operator. And when we did this, we could use the same anti-commutation rules as we had with the standard creation and annihilation operators. But later today, we are going to go back to these because it's a little bit cumbersome to deal with these operators, because sometimes it's difficult to keep track of when is it a creation operator and when is it a annihilation operator. So these were the definitions which we had. And the only contraction which was different from zero was this one. All the other ones are zero, so I'm not going to list them. And then we had the standard anti-commutation rules of B alpha, B beta, which was equal to B alpha dagger and B beta dagger. And these are both zero. So the only non-zero contraction was that one. And we looked at some examples of operators last week. So let's quickly remind ourselves about the operators which we had last week. So one of the operators which we rewrote in terms of this new set of creation and annihilation operators was the number operator, which simply gives us an expectation value, the number of particles you have. And the number operator was something which we had written like this. And we had an A alpha like this. And we could rewrite this one in two sums, where we now have an alpha, which sums over states above the Fermi level. And then we had a minus sign of alpha less than equal than F. So these are for whole states or states below the Fermi level. And then we had plus N, n is just a scalar, the number of particles which we have. So this was just a rewrite in terms of the new operators. And then we calculated specific states and expectation values. So we could define a state which we labeled as a state with an alpha below here. We're going to change this notation a little bit later. So this was the same as a B alpha. So we create a hole. So this is alpha is now less than F or equal to F. And this creates a hole in the vacuum state, the reference vacuum state, which we have chosen. So we would call this a one-hole state. So in principle, this is an n minus 1 particle state. This is when we use these operators. So later today, we're just going to go back to the other ones, and that's going to change the type of contractions which are non-zero. And that will give us a somewhat more compact type of notation. Another operator which we could define, or another state, was a state which looks like this, an alpha, and then we have a beta here up. So beta is larger than the Fermi level. So we have in the superscript is states above the Fermi level, and the subscript is for states below the Fermi level. So these were just notations which we had last week. And this was given by a B. So we create a state above the Fermi level, and we destroy one below the Fermi level. So we create a hole. So that's the kind of language which we end up using. And this is something which we call for a one particle, one hole state. In this specific case, we remove one state from below the Fermi level, and we put a new one on top of that one. So this is still an n particle state. And then we could continue like this. We can create 2 particle, 2 hole, or just a 1 particle state, 3 particle, 3 hole, etc., etc. So this depends on the type of creation and annihilation operators which we're plugging in. Now, another operator which we rewrote last week was the Hamiltonian, the part of the Hamiltonian which deals with a single particle piece. So let me just remind you a little bit of that one. And in the lecture slides, you will find a rewrite of the two-body operator. This is not a very exciting exercise, because then you have 2 creation and 2 annihilation operators, and you have to take into account sums above and below the Fermi level. And you will find the solution to that one in this lecture slides. So I'm not going to go through that one, because that's just an exercise in rewriting a quadruple sum in terms of sums over states above and below the Fermi level. But the one-body operator is a little bit simpler, and that's going to contain the basic message which we need today. So these 2 operators, we're going to play around a little bit with them today. And this is something which we then rewrote as an alpha, and then we have this matrix integral with a B alpha dagger, B beta. Then we had plus, and we had a sum of alpha larger than F and beta less and equal than F. And that contained 2 contributions, alpha of H0 of beta. And this had a B alpha. So we create a particle state and we create a whole state, plus a beta of H0 of alpha. And then we had a B beta and a B alpha. And finally, there were 2 additional terms. One, which now included a sum over states below the Fermi level. And that had an integral, which starts with a beta here and ends in an alpha. And then it had a B alpha or B beta. And finally, there was a constant, like the number of particles present in the system. And this is something which is going to be extremely useful when we now are going to calculate expectation values. So this contains a sum over this alpha of H0 of alpha. And in case alpha is an eigenbasis of H0, we could replace this with a sum of epsilon alphas. Now I'm going to give a name to this term here. So this is going to be the sum over the non-interacting energies. So if we have a specific computational basis, these computational bases is now going to give us a term when we sum up everything, which I'm going to call epsilon zero. Later, you will see that there is a similar term from the two-body interaction, and that will define the energy of the expectation value of the vacuum state to the vacuum state. And that's just a constant which we just can carry with us in the calculations. And you will see how that comes through now. So this is basically what we did last week. We manipulated the sums, and then we got the sums for states above the Fermi level, but we kept these creation operators and annihilation operators. The thing I want you to note as well is that all these operators here are in the form which we call normal ordered. So normal ordered means that we have the creation operators to the left and the annihilation operators to the right. So that means that when we act on the vacuum state with this, we will get this one acting on the vacuum state, that will just give us zero. And you see the same thing with the number operator. So everything is written in a normal ordered form. And that's an important aspect of what comes now. And then we have this constant, which is now here just simply the number of particles. So we're going to practice a little bit, but I'm going to introduce a new notation for the way we label the single particle states. And that's a notation we will use for the rest of the semester. So let's bring up that. And this is something which is traditional, has been a tradition in quantum chemistry, atomic and molecular physics, but also in nuclear many-body physics. So I'm going to introduce a new label for single particle states, SP states, so that when you see different terms coming in, you will immediately know that this is a state below the Fermi level, and this is a state above the Fermi level. So what that means is that if we look at the way we have labeled the Fermi systems, so we have a Fermi level, and then we have all these states below the Fermi level, which we have labeled as whole states. So that means that when we create a hole, we're actually vacating one of the fermion slots. And I'm going to label these with letters I, J, K, L, etc. Now, we are not going to exhaust this lettering because in many of the applications which we end up with, we have at most 3 particle interactions. So that means that we can keep this kind of labeling. You see quickly that if we move on, we will actually exceed in the alphabet the kind of letters we have. So this kind of labeling is simply due to the fact that normally we end up with perhaps 4 particle for all excitations at most. And then we have the states above the Fermi level, which are normally called particle states. So in some textbooks, you will find these labels as quasi-particle states, but we will just simply label them as particle states. It's a little bit kind of a misnomer because we have particles below the Fermi level, which can fill in those states, and particles which can fill in states above the Fermi level. But this is a kind of notation, which is, so these are particle states. And I'm going to use letters A, B, C, D, etc. And then I'm going to have a common denominator for all these states. And then I'm going to use letters P, Q, R, S, etc. So this is a kind of labeling which I'm going to use now. So what when we now look at these, the first type of creation and annihilation operators which we have, so that means that when we look at the operators, so we are going to go back to A alpha dagger and A beta, but we are now going to redefine them like this. So we have the contraction AP and AQ. So if we look back at what we did with these particle hole operators, this is going to be delta PQ if and only if P and Q are states above the Fermi level. So this is one of the contractions, the standard contraction, which we have always been using. And in our previous notation, this contraction here has always been 0. But now we're going to redefine it. So that means that this is going to be different from 0. if P and Q, both of them are below the Fermi level. So it means that we will reintroduce the same operators, but we will have a subscript which labels whether these are particle states or whole states. And the reason for that is that if you go back to these operators which we had here, these particle hole operators which we introduced, you see now that if the states, if alpha and beta are below the Fermi level, then this guy here, this one changes into an annihilation operator, and this one changes into a creation operator. So if you look at this for states below the Fermi level, what we would have, so let me just bring this in here. If I now introduce this new notation, I would then have an AI dagger, an AJ, and if I do that contraction, this is now going to be different from 0. Now, one thing which you will see when we go back to this notation is that when we perform the contractions, and this will come through in the examples you're going to see now, when we perform the contractions, we will get something, if we look at this term here, which will give us a minus sign. So this is the equivalent of us now changing to the back to the old operators, but where I put indices I and J here, explicit ones, and then when I perform this contraction here, there will be a minus sign. So we are going to associate with whole states. When we are going to look at diagrams, we are going to associate with whole states a minus sign when we perform the contractions. But we, in the notation which we have here, we are not putting the minus sign here. But the minus sign will come when you do the contractions. And when you look at the diagram, and you have to add to the diagram rules a minus sign in case the states are whole states. So it takes some time to digest this because I introduced these new operators, but then I want to go back to these because these are going to give us a more simplified notation. So that means that if I look at the number operator I had, so remember now that this number operator was given as the sum over alpha larger than F, and then I had my B alpha of B alpha here, this is a number, and then there was a minus sign for the states below the Fermi level, of B alpha dagger, of B alpha, and then I had plus N. So this is something I will now rewrite. Going back with the old operators, I will rewrite that as a sum over P. So there's only one label here because I'm just having a single sum. And then I'm going to have this strange notation here, which I later I'm going to take away. So if you look at that textbook by Shavit and Bartlett in chapter 3 and 4, they define this as a normal ordered set of operators. Ordered with respect to new vacuum, just to distinguish that from what we introduced in the beginning when we looked at the true vacuum, with respect to new vacuum. This is to distinguish what we had before with what is going to come now. And then we need to add this N here. And this N is normally called a reference value, because that's going to be the number of particles which you have in a new vacuum state. So this is the reference value. And in this particular case, it refers to the number of particles you will have in the new vacuum state. So what we are doing now is just to redefine the Hamiltonian with respect to a new vacuum. Now, if you look at this guy here, let's now calculate something with it, with this new operator here. So that means also that when I look at a state like this alpha beta, which we defined earlier, this is going now to be rewritten. And this is a notation I will keep using. So there's going to be a whole state here, and there's going to be a particle state here. And this is going to be defined as an A dagger. So I create a particle above the Fermi level, and then I take away one particle below the Fermi level. and this is going to be given like this. And we call this, again, a one particle, one whole state. But now this is explicitly defined in the sense that what we have is a particle state here and a whole state here. So if we use the old definition of the operator, this one removes a particle below the Fermi level, and here I create one. So this is what we would call a one particle, one whole state. And if you go back and make a drawing here, it means that you have all these states, and these are filled, and then there is a state I here. So these are filled up to the Fermi level. So we have a Fermi level here, and then we have all these states above, and then there's a specific state A. So we remove a hole here, and then we fill in a slot above the Fermi level. So this is an example of how you graphically would represent a one particle, one hole excitation. In principle, you have an infinity of these because the single particle states above the Fermi level, if you have a standard basis like the hydrogen-like basis, the harmonic oscillator basis, you have an infinity of states. So this is our, remember, this is our computational basis. Okay, so that would be that specific state. So what we're going to do now is simply to calculate this expectation value for this state here with this new definition where we have an I of A. So when we look at that one, this will be a sum over P, and this runs over all possible particle states. And then I have my phi 0, and then I have my AI dagger, AA, and then I have my operator AP, and AP here, and then I have my A, and then my AI acting on phi 0. And now what you see when you perform the contractions here, you can now perform a contraction between these two guys. And remember now that we are using Wick's generalized theorem, which means again that we can only link operators which are, take contractions between operators which are normal ordered. So everything you see here, all the different pieces here, this is normal ordered, this is normal ordered, and this is normal ordered. So the final one here is given by that one. So that gives us, when we set up the contraction, a delta II. We perform this contraction and we have a delta AP, and then we have a delta AP again. And there is obviously a term which I haven't listed yet, which is given by this term phi of I. Let me just put it on the other page. Because in here, we also need to take this number n, which is just a constant. So this is the operator, which you see here, but the operator contains also this term here, which is just a number. Then the next contraction, which I can take, so let's just add that next contraction. So I would have an AI of AA, and then I have my AP, dagger, AP, and then I have my AA and my AI here. Now, the next possible contraction is that I can have, which is now something which would be defined by the new rules which I have introduced, since these are whole states. That means that I can actually contract this one with that, but then I can contract this one with that one. Now, you remember that one of the rules which we introduced was that if we have such crossing lines when we perform the contractions, that gives rise to a minus sign. And then we have the final one, which will be A with itself. So this would give us minus delta I of P, and then I have a delta I of P, and then a delta AA. And the final term, when we add things up, would be a phi AI with just this number, phi IA. And this is just given by the number itself. This is just a scalar. So what I'm getting now is three Kronecker deltas here. This gives us just one, like that. The previous one gives us just 1, and it's picking out one of these terms. So it's 1 minus 1, 0. And when I add up everything, this is equal to n, the number of particles, as expected, because this state here, phi of I of A, is an n particle state. So we are counting simply the number of particles in that state. And we see now that this gives us just the number of particles, as it should be. If I were to calculate, and I leave this as a small exercise for you guys, if I were to calculate this one, A of n, what you will see then is that you will get n minus 1, because you have removed one particle. So this operator here, this one, is actually A of I acting on phi 0. So we have an n minus 1 state. And then when I take the brass side, I also have an n minus 1 state. And when you perform all the contractions, what you will get then is simply that you have n minus 1, which is the number of particles which you have there. So let's practice a little bit more. And so what's going to follow now is actually a series of applications. And just to convince you of the compactness of this formalism. So another thing which we are going to look at now is the calculation of an expectation value of this phi of I of A of H0 of phi of I of A. Now H0 in the new formalism is actually going to be given by a double sum of P and Q. And I have this normal ordered operators with respect to the new vacuum. And later I'm going to take away these curly brackets because it will be obvious from the context whether this is a set of operators ordered with respect to a new vacuum or with respect to the true vacuum. And here I have to include this integral of H0 of Q. But then I had an additional term. If you now go back, so if you look at the definition we had for H0, so H0 contained now set of normal ordered operators, normal ordered, there's a minus sign here. So I'm going to bring everything here into that specific expression you see, and then there is an additional term, which is just a constant. So I'm going to rewrite all these terms here, just in terms of the first term you see here, because that contains a set of normal order operators, plus this epsilon 0, which is then just the sum over these single particle energies. So this will be a sum over I. So I is below the Fermi level. And I will normally suppress this less than F. So I will normally just write I. And this is given by I of H0 of I. And clearly, if I is a computational basis, which is again an eigenbasis of H0, this will simply be given by the single particle energies epsilon I, as we've been calling them previously. Okay, so let's now look at the set of contractions we can get when we take this specific operator with this state, A of I, and then we are going now to have, so let's just rewrite it a little bit. We take this one. So we're going to get the following. We have a sum over P and Q. We have this matrix element, H0 of Q. And then we will be having the following type of contractions we need to deal with. So we have an A of I dagger, A of A, AP, AQ, multiplied with A of A dagger, A of I, and phi 0. So I just wanted to go through some of these, examples so that you get a feeling of how useful this formalism is. And it makes it much simpler because now you don't need to deal, if you have 100 particles here, you don't need to deal with all the 100 particles being contracted with this guy here. We are simply looking at a new representation, and with the new anti-commutation rules, this is going to simplify life considerably. So let's now look at the possible contractions we can have. So I have an AI dagger, and I'm going to write it in this more compact notation. AQ, and then AA and AI. So here, I can obviously, if these are particle states, then this is non-zero. And then I have this contraction here. But then I can let the operator move into the whole states. So keep also in mind that if I do a contraction of the type like this one with that one, that is automatically zero because A and I are different. I also know that if I do this contraction, that is zero. If I do this one, that is zero. If I do that one with this one, that is zero. And this one with that one, that is zero. So I'm only listing the possible non-zero contractions. So this term is going to give us a delta AP, a delta AQ, and a delta II. If I look back at the matrix element I have, this means that what I will get, or the integral as we've been calling them, this will now give us a contribution which goes like times, and then I will have an A of H0 multiplied with A. Then the other contraction, the only other one, which is non-zero, is going to be the following. And in this case, I'm locking this one. And keep in mind now that we have explicit indices A and I, which refer to states above and below the Fermi level. Now, the only contraction now is us taking this P to that one, and this A, I to Q. Now, in this case, in order to get the contractions right, we will obtain a minus sign. So that's going to give us a minus delta IP, delta IQ, and then I have a delta AA. And this is multiplied with an integral of I H0 of I. Then finally, if I look at the constant term, which I have this epsilon 0, this one is just a constant. So that's just going to give us an epsilon 0. So when I collect everything now, and if I call this one for epsilon I, little epsilon I, and this little epsilon A, I'm going to get the final answer that this phi of I of A of H0 of phi of I of A is equal to epsilon A minus epsilon I plus this epsilon 0, the reference energy. This is something which we will find extremely useful later when we are going to set up the first many-body method, which will be full configuration interaction theory. And in that specific case, we can actually almost read off the expressions for the matrix elements, which we are going to need in order to be able to diagonalize. So the thing now is that we have a much more compact way by which we can calculate specific expectation values. And you can also, if we take another example, if we now look at this specific expectation value or transition probability, if we take this one, what you will see then is the following. If we now do the calculation, you will have a sum over P and Q, the operator, and then we have the state phi 0, and there is nothing there, so we have AP dagger, AQ of AI, of AA and AI. And this is multiplied with P, the integral, like this. Now, if you now look at the possibilities which we have, then what we could have is actually something like this. This is non-zero. And then we can have this one. So that this would give us a delta P of I and a delta Q of A. So that means that we are going to get a contribution then, which is given by the integral P of H0 of Q. Now, sorry, not that one. I have to put in the letters here. So what I would get then would be P being given by I and H0 of A. Now, if A is an eigenbasis and I are eigenbases of H0, this is automatically 0. If we have H0 acting on A is equal to an epsilon A times A, then this quantity here requires that we have delta IA with an epsilon of A, which is not possible because I is different from A by construction. So in case the basis we're using is the computational basis defined as the eigenstates of H0, then this will be automatically 0. So that's just one thing to keep in mind. And this is the only possible contraction, because if I try to take this contraction, this is obviously 0. If I try to take this one with that one, that's obviously 0. This one with that one would obviously be 0 here, etc., etc. So this is actually the only possible contraction we can have, which is non-zero. Now, there's an exercise this week where you ask to rewrite the two-body operator. And this is something which you will have to do on Friday, but I just wanted to set up the answer here. So what you would need to do then for the two-body operator is simply to manipulate these different expressions. And you can easily then see that it turns into the following expression, H of I. And we can write it with or without anti-symmetrized matrix elements. But now I'm going to use anti-symmetrized matrix elements. So we are going to have a sum of a PQRS, and then there is an integral PQV of RS. And then I'm saying that these operators are normal ordered with respect to the new vacuum. And as I said, later we are going to interchange that and just leave out this curly brackets. So I'm going to relabel this term here as a V of N. So that's a new operator. When I do a rewriting, as you will see in that exercise, you will get some additional terms. You will get a term which contains a triple sum of PQ, where one of the states has been defined to be a whole state. And I will have the same matrix element, P of I, of V, of Q of I. And these are anti-symmetrized matrix elements, so they contain the direct term and the exchange term. But now this is a one-body operator. Plus, and then there is a constant term, 1/2, where I'm summing freely over I and J. And this is nothing but the vacuum-to-vacuum expectation value, or this phi 0 state, which we have defined as a new vacuum, anti-symmetrized. And this is the same thing which we calculated in the very beginning of the semester. This will be the same as the expectation value of this ansatz we have for the ground state of the system, or the new vacuum state, with respect to the two-body interaction. Now, we are going to give that a name, and we are going to bring this together. So this is a definition we will keep. So we are going to define something we call the reference energy. And this reference energy is simply this epsilon 0 plus this term phi 0 of H of I of phi 0. And you remember that this term which you have here is nothing but this expectation value of H0 of phi 0. And this is something which we calculated in the very beginning of the semester. Now, this is just a number, it's a constant. And what we have done is simply to rewrite the Hamiltonian with respect to the new vacuum. So when we now are going to calculate the expectation values of these particle Hall states, or with the vacuum reference state, or with other types of excitations, this will always come out as a constant in the expectation value. So let's now look at how we can rewrite the Hamiltonian. So I define this V of N, But what I'm going to do now is to bring in this operator here, which is a one-body operator, but with a two-body matrix element. I'm going to add that one to, I'm going to add the one-body part which you have here together with that one, and I'm going to redefine my one-body operator. And this is something which becomes extremely useful when we do density functional theory or Hartree-Fock theory, because that defines a mean field which all the other particles sees. So let's see how that comes through, and then we take a small break. So I'm going now to use the old definition of H0, which contains this term. And I'm going to add to that one this new term, which comes from the two-body interaction, but normalized to the new reference state. That means that what I will do now is to redefine H of I, no, H, the Hamiltonian which we had. I'm going to redefine that in terms of a one-body operator, F of n, plus that two-body operator, which we had in the previous slide. So let me just remind you of that one. So this is the term which you see here, this specific term, only that one. And then I'm going to have this E0 reference, where this term, as I said, is nothing but phi 0 and the expectation value with phi 0, where that is an ansatz for the vacuum state. This phi 0 is not an eigenstate of H. Just keep that in mind. So we have defined this V of n, but now we can we can now define this guy, and that's simply going to be given by the sum PQ of I. I have these normal ordered operators with respect to the new vacuum. But I have this matrix element, P of I, of V, of Q of I, anti-symmetrized, plus the sum P of Q, and then I have the traditional or the old one-body piece, where this now had this specific integral of H0 of Q. And what I will define now is a new integral of P of little f of Q, which is now simply going to be given by the sum over I. So these are states below the Fermi level, remember that. And then I'm going to have a P of I, of V, of Q of I, an anti-symmetrized matrix element, plus P of H0 of Q. And again, if P and Q are different, and at the same time they are an eigenbasis of H0, then this last term would be 0. If P and Q are different, and if they are an eigenbasis of H0. Now, what you see now is something which becomes interesting. This sum here runs over all states below the Fermi level. So if you now are thinking of all these states being filled up with particles, then this P and Q, they will be seeing all the other particles. So you can think of this thing here as a field which is being set up by all the particles below the Fermi level. This P could be a particle state, or it could be a whole state. And then in addition, we have the contribution from an external potential and kinetic energy, which affect the motion of the particle. So this piece here can contain only kinetic energy, or it could contain an external potential like a harmonic oscillator, which confines the motion of the particles. But then we are correcting this with a mean field, which is set up by the contribution from all the other particles. So you could think of this now as a, let's say you have a system here, which now has all these single particle states, which are being set up below the Fermi level. And then you have a state outside here, which we give a label P, and that sees and interacts with all these guys, because this sum here runs over the interaction between this state P, which could be a state above the Fermi level, with all those below the Fermi level. So it's a way to represent a correction to the external potential, which confines the motion. So if you have a particle in a gravitational field, that would be an external potential which confines the motion. You have kinetic energy, but then these particles are not alone and they see a medium. So we often call this for a medium correction, or a mean, simply a mean field addition to the external potential the particles moving. So if there were no other particles, this piece here is obviously zero. And then you're just moving in an external potential which confines your motion. This piece which you see here becomes very important now when we are going to look at, let's say, Hartree-Fock theory or mean field theories, density functional theory, etc., etc. So these are just redefinition of the Hamiltonian. So after the break, we are going to run some examples and see how easily we can actually calculate expectation values and transition probabilities now with this more compact expression for the Hamiltonian with respect to a new reference state. So what we're going to do now is to use these definitions and look at selected examples. And after we've done with that, we have the basic machinery to start with our first many-body method, which is going to be what's called full configuration interaction theory. And after full configuration interaction theory, we are going to move on to Hartree-Fock theory. So full configuration interaction theory is a theory which is actually pretty simple, and it allows us also to introduce the expansions of the true state in terms of a computational basis. And that brings us back to the basic linear algebra of unitary transformations, which is a central feature in many of the things which we will be doing from now on. But what we have done now is to redefine the vacuum state. And I also wanted to remind you that this phi zero, this is an ansatz we have chosen. And this phi zero is normally the solution of the non-interacting part of the Hamiltonian. And it's often something which we would choose if we believe that this non-interacting part of the Hamiltonian is highly relevant for the physical description of the system. Okay, so the other thing which we introduced was this new operator here, which now, with respect to the vacuum, to the new vacuum state, it contains a term which we dubbed as a mean field contribution to the external potential plus kinetic energy, which we use to describe the motion of a given particle. And also keep in mind that the computational basis is now given by these states here, which normally are chosen to be eigenstates of this H0. And from that, we can build a many-body state based on these single particle states. And that is one of the standard recipes in many-body physics. But what I want to do now is just to run through a series of examples. And let's now look again at this specific state, which we call the one particle, one hole excitation. So what now we want to do is actually to calculate the expectation value over Hamiltonian, but now using the new representation of the Hamiltonian in terms of these normal order states with respect to a redefined vacuum state. So we would then have this V of n, and then we have this new operator F of n, plus this reference energy. Now, the last one is just a number. So that gives us just the reference energy. So that would be something which we will carry with us. And often when we run calculation, you can subtract it away because it's just a reference energy you can add back at the end. So what we will be interested in now is to calculate with this Fn, so which we then can rewrite in this compact way as a P of Q. And then it contains these integrals, which we defined before the break. times this normal ordered set of operators, like that. And this contains both this mean field and the term which we introduced in the beginning of the semester, this H0 term. And finally, we need also the V of n. But let's take the f of n piece first. So with f of n, when we calculate the expectation values now, what we need to do is simply to calculate this I of a of f of n, of phi of I of a. And this is going to be given by the sum of a p of q. I have the integral. And now my basis q, is not necessarily an eigenbasis of f. Okay? So we assume that p and q could be an eigenbasis of H0. But this new operator, which we have defined, doesn't need to have p and q as an eigenbasis. When we are going to introduce Hartree-Fock theory and then density functional theory, then this p and q can be eigenstates of f. So just think of that when you do Hartree-Fock theory, which many of you may have heard of, or mean field approach, then we are redefining the single particle basis so that that becomes an eigenbasis of this operator. But it doesn't need to be. So when we now write this out, what we have is the expectation value with all these operators. We have an AI, AA, and then we have AP, AQ, and then AA of AI, and phi 0. And this is a term we need to look at now. So if we now look close at that term, this is pretty close to what we did before the break. And now I'm just going to set up the contractions which are non-zero. So we never care to write down the zero contractions of A of I. And one of the contractions we have is this one, which we also had before the break. And then the other contraction is actually A of I going to AQ, but then we get a minus sign for here. And then we have the final one with AA going to AA. So this would give us, again, delta of II, and then a delta of PA, and a delta of Q of A. Whereas here we have minus delta AA, and we have a delta of IP multiplied with a delta of QI. And this will contain integral where we now have A of F of A. And this one would then give us, in addition, it would give us this term, which is now I of F of I. So when we collect these terms, we are going to get the following. So this will give us epsilon A, if we assume that this A and I basis is an eigenbasis of H0, and then I'm going to have a sum over J, and this sum gives now this correction to the field which A moves in. So this should be J, anti-symmetrized. And then I have a minus of epsilon I minus J, and then I have Ij of V, Ij, and this is an anti-symmetrized matrix cell. So in our previous life, when we didn't have this vacuum state, this term which you see here, this one, would come from an expectation value of the two-body operator. So if we hadn't redefined the vacuum as we did, we would have gotten this term, but it would have come from your two-body operator here, not defined with respect to the new vacuum. And the one-body operator would simply have given us epsilon A minus epsilon I. So this comes actually from our two-body part of the Hamiltonian. But we have put it into this new redefined one-body operator. And that gives us a much more compact way for which we can run the calculations with. Then what we need to calculate is the expectation value of the two-body operator which we have. So the final term is this one. So we will have a sum of a PQRS. That's going to be an integral of RS. And we write this in terms of anti-symmetrized matrix elements. There's a factor 1/4. And then we have now the phi 0. And then I have my A of I, A. And then I have the operator, the two-body operator. Of phi 0. Now we can start to look at contractions. And one contraction which is non-zero is going to be this one with that. And I'm going to have this one with that one. That is going to be non-zero. So these are particle states. Remember A, so P must be a particle state then. And then I have my whole operators, which means that what I would need to do now, if I look at this operator which you have here, that if I try this contraction, that is automatically zero. But I could actually try this one. That would be non-zero. Similarly, I would have this one with that one. That is a non-zero term. So that means that when I do the final operations here, I can contract this one with, oops, something went wrong here. Now this one, and then I can actually perform this contraction you see here. And finally, I would have this one with that one. Now, when I shuffle around the operators, this is actually going to give me a minus sign. And because we have these crossing lines with the whole lines. So remember now that when I take contractions with whole operators, that gives rise to a minus sign. And in this specific case, you can see now that there's a minus sign. And when I now look at these possible contractions which I have, in total, there will be 3 more possibilities. This term here gives me minus, and there's going to be a matrix element which will have a factor of 1 divided by 4. When I set in the Kronecker deltas, you will see now I will have A, and then I'm going to have a R to A, but I have AI to S. So that means that when I put it up here, I get a state I here. I will have my A, which contracts with R. And then I have my I here. So that's the matrix element which I will get. Then, when you look at the contractions here, there are 3 more possibilities, plus 3 more. And they will give rise to different types of, so this is an anti-symmetrized matrix element. And they will give rise to 3 matrix elements which are similar to that one. So what we need to keep in mind is that these matrix elements have a specific symmetry. So this is going to be equal to minus IA of V IA. It's going to be equal to this specific matrix element here. It's going to be equal to IA of V. So these are all anti-symmetrized matrix elements of IA, anti-symmetrized, etc., etc. So when we do all this contraction, we can choose now, and they're all going to be equal, except that there will be either a minus sign or plus sign. So you can then decide whether you want to have a minus sign or plus sign. So you can write it if you want to have a plus sign. You could then take this element. If you have a minus sign, you will get 3 more terms which have the same expression. So they all add up, and you will end up with a specific matrix element here, where you now have performed all the possible contractions. So that means that when I collect everything here, I'm going to get an expectation value for this term here, phi A of A, and where I have my Hamiltonian H of phi IA, which then will be given by the following expression. So I have epsilon A minus epsilon I. These are the so-called non-interacting single particle energies. I will get this additional term plus, and then I have a sum over J, and then I have my A of J of V, A of J, anti-symmetrized, minus, and then I have my J of I and J and V, I and J, anti-symmetrized. And then finally, and now I'm just using the matrix element with a plus sign, and then I have an I of A, anti-symmetrized, plus the reference energy. So the first four elements which you have, the first four ones, they come from the one-body operator, and they represent now the non-interacting single particle energies, plus a contribution from a mean field which modifies the motion of a single particle. And then in addition, there is a two-body matrix element. And these are the expectation values which we get for that specific state. I invite you to try out to calculate phi I with H and phi J, so they are different. I leave that as a small exercise to you guys. We can also now look at other types of transition probabilities or matrix elements. And one of the things we can look at is actually a two-body state. So we can have a transition from the vacuum state, phi 0, to a two-particle, two-hole state. These are also elements which we will need when we are going to develop our first many-body theory, which is full configuration interaction theory. Because then we are going to set up a Hamiltonian matrix which will be defined by this basis of Slater determinants. So this specific state, phi ij, is a two-particle, two-hole state, exactly. So this is two-particle, two-hole. And this will be given now by AA, AB, the creation operators for the particles, AJ and AI, acting on a vacuum state. Now, when you now look at the one-body operator, this is going to be something we can easily see what the contribution should be. So let's calculate this one. So this is the transition from the ground state to, or the ansatz for the ground state, to a two-particle, two-hole state. So let's take a closer look at the different terms. So the reference energy term, E0 ref, multiplied with phi ij AB, that has an obvious answer, right? That has to be 0, because these are orthogonal states. And you can quickly see that because what you're going to calculate here is phi 0, and then you have AA, no, sorry, this is a transpose state, so it should be AI, dagger, AJ, AB, AA, acting on phi 0, and this is automatically 0. Because we are trying to destroy a state A which doesn't exist in phi 0. So this is automatically 0. So we don't even need to consider that one. If we now take the one-body operator, if we take the Fn term, what we get then is the following. So we have a sum of a P and Q, we have the integral, and now we have this F of Q, and then we need to look at this phi 0, and then I have an AI, AJ, and then I have an AB, AA, and then I have my AP dagger, AQ, multiplied with phi 0. So if you look at this one, what would you expect for value here? If you now try to set up the contractions and find eventual contractions which give something which is non-zero. So if you just take a look at that one, let me just rewrite it quickly. So we are going to have these operators, which we now need to contract. And keep in mind that we have Wick's generalized rule. So we cannot take contractions between the same chain of normal ordered operators. So what would you expect here that this should give us? If you think physically, so you can create a one particle, one hole excitation with this operator here, right? So when this one acts on this state, what you could create, if P is a state above the Fermi level and Q is a state below, you could create a one particle, one hole state. But then you want to match that one with a two particle, two hole state. So what would you expect then as a result? So it would be, suppose now, so you have AP, AQ acting on phi 0. So if Q is a particle state, this is automatically 0. If Q is a whole state, then I can actually remove a particle, but then P has to be a particle state. Because P then, if P is included in here, then you could actually, so you could actually reproduce phi 0. You can do that. So this can give us something like phi 0. If Q is a state below the Fermi level and P is a state below the Fermi level. Okay? Because then I would remove one particle below the Fermi level and the next one could add it. And that would just give me phi 0 again. Alternatively, P could be a particle state and Q could be a whole state. And then I would get a one particle, one whole state. I'm just going to write it like that. But what you have on the brass side is a two particle, two whole state. So what you would end up taking the overlap of is either this or two particle, two whole with a one particle, one whole. So these are the only possibility if you think physically of what these operators are doing. So this specific operator here can actually bring you back to the vacuum state, the reference state, or it can create a one particle, one hole excitation because it's a one body operator. And if you then look at the final overlaps you're taking, what should they be like? It's an obvious number, right? So this is 0. So this one body operator does also give us 0 contribution. So the reference piece doesn't give us anything. And then we also have the one body part, which gives us 0. Because at the end, we are trying to link a state with another state and take the overlap between these, and these states are different. So I hope you see, I'm spending some time on this because when you look at many of these contractions, you can try to develop your physics insights. And so the way we interpret the different operations is in terms of excitations. So instead of you in first quantization where you let the particles interact with each other infinitely many times, you will now have an infinity of one particle, one hole excitations. And that's the way we actually reinterpret the physical systems in second quantization. So that's the kind of language which we keep using. And the jargon here is then that this guy here, when it acts on this reference state, it can bring you back to the reference state, or it can create a one particle, one hole excitation. And then depending on what you have here, you can then have 0 or non-zero. So if you go back to a one particle, one hole excitation, then this can be non-zero. But if you have a different state, then it has to be 0. So if you then go to the two body operator, then we would have something which looks like this. So we would have 1 divided by 4. We have the sum of a PQRS, and then I have PQ V of RS, the anti-symmetrized matrix element. And this is multiplied then with phi 0, the vacuum state. And then I have my 2-particle, 2-hole excitation of A, B, A, A. But now I have an operator here, P, A, Q dagger, AS, and AR, acting on phi 0. Now, if you now think physically, what could happen is that this guy here actually makes a 2-particle, 2-hole state. And then on the bra side, you have a 2-particle, 2-hole state. So that means that the overlap can be non-zero. If this, on the other hand, brings us back to the vacuum state, then that will be 0. Because if this brings us back to the vacuum state, then you have phi 0, and then you're taking the overlap with a 2-particle, 2-hole state. If this creates a 1-particle, 1-hole state, then that overlap would also be 0. So it means now that in order for this to be non-zero, then the operator from the Hamiltonian must create a 2-particle, 2-hole state. Because that's the only thing which will give you a non-zero overlap. And then the rest here are just constants, which you multiply with. So when you now look at the contractions which you can have, so we could now have the state A being contracted with that. That is possible because this is a particle state A. So remember now that the only non-zero contractions, if I have AP, AQ, this is equal to delta PQ if PQ are larger than F, if they're particle states, and A is a particle state. And similarly, the other contraction, which is non-zero, through the way we have redefined them, is this one, but then P and Q have to be less than the Fermi level. So that contraction is fully possible. And then I can contract this one with that one. And we know that everything else here with A and B, if I try that one, that's 0. If I try this one, that's 0. If I try this one with that one, that has to be 0 because it's a particle state with a whole state, etc., etc. So you see now that if I keep these guys fixed, what I can have now are contractions of this type, and here, like that. That's fully possible. But then each one of these, this one gives me 2 possibilities. I can interchange them. And this also gives me 2 possibilities. I can interchange them. And these are the only non-zero contractions which I can have here. And when I bring everything together, what I will get typically from the first term here, I will have a delta AP multiplied with a delta QB. I will have a delta SJ, and I will have a delta IR. Multiplied with the matrix elements where I have A, B, and then V. And then I'm having the next piece, which will be I and J. And this is an anti-symmetrized matrix element. Now I have a factor of 4 here, 1 over 4. I will get 4 such terms, some with minus signs, some with plus signs, but then I can use the symmetry of these interaction matrix elements. So if I add plus 3 more contractions, so at the end, what we will get as an answer is actually A, B, V, I, J, anti-symmetrized. This is the only term which survives. So if we summarize, when I calculate this specific expectation value, AB with H, and then I take the vacuum to a 2-particle hole state, this kind of transition probability, this is simply going to be given by AB, V, IJ, anti-symmetrized. So I leave to you a little bit to check that you get 3 more terms, which are non-zero. And then you will use the symmetries of these anti-symmetrized matrix elements. That means the symmetries which you see here. And then you sum up these terms, and then you will get 4 matrix elements which are the same, and I kill the factor 1 divided by 4. So that means that this specific transition probability just gives us that matrix elements. So if you now have 100 particles in your vacuum state, if you did this without redefining the vacuum state, you would actually look at all the possible permutations. So you see the advantage of redefining the vacuum state. And that gives us a more compact notation. And also from a calculational point of view, this is much easier to handle with. And so that will be that specific piece. And I'm going to give you a kind of a small exercise, or rather let's take that one together. And then I'm just going to give you 2 more exercises. So one of these exercises is pretty easy. And you can see that immediately. If I take a 3 particle free hole state, and I calculate the expectation value, and I have only a 2-body operator. So this is what we would label as a 3 particle free hole state. What would you say the expectation value should be here? Well, not the expectation value, but the transition probability here.
0.
0, exactly, because you have now only a 2-body operator, and there would be a set of creation and annihilation operators which would not be contracted and give something which is non-zero. So this is automatically 0. And let's just do a final case, which is going to be very useful when we study Hartree-Fock theory and the mean field theories. And this would be this matrix element here. So in this particular case, we know that when we look at the reference piece, that is just a constant. So if we do the reference E0 ref, this would just be a constant E0 ref, and then I would have a phi 0 with phi I of A, and that has to be 0 because that overlap is 0. Then the next piece we need to look at is this Fn operator. And in that case, what we have is the following. So we have a sum of a PQ, and then we have this matrix element P, or this integral actually, it's more correct to say it. No, not H, but this is going to be F. And then I'm now having to multiply this with phi 0. And then I have my AP, my AQ dagger, AA, and AI of phi 0. In this specific case, what we see now is that the only possible contractions would be Q with A and P with I. All the other contractions are simply 0. Because I cannot do Q with I cannot do A with I. That's not possible because one is a particle state and another is a whole state. Also, we would violate Wick's generalized theorem. So this is the only possibility which we have, which is non-zero. And that gives us, when we now bring in these contractions, that's going to give us a P, which is going to be equal to I, and this is going to be F, and this is going to be A. And this will again be equal to I of H0 of A. And if A and I are eigenstates of H0, this is automatically 0. But we can just leave it like this, and then we have a sum over J. These are states below the Fermi level. And then I have Ij, V, Aj, anti-symmetrized. Now, when we are going to do Hartree-Fock theory, so I'm just anticipating what it means mathematically. So when you do a Hartree-Fock calculation, you are going to find a unitary transformations which drives these matrix elements to 0. So that means that when you solve the equations, what you end up solving is to solve an equation where you now are going to drive these specific matrix elements to zero. So you're going to define a field where these will be zero, and you will construct a basis which is going to be an eigenbasis of this operator f. So if I with A, this specific contribution, this integral is zero, you're then constructing a new basis, which is going to be an orthogonal basis, and which is going to be an eigenbasis of this operator f. So Hartree-Fock theory, which we will start looking at from full configuration interaction theory, where we are going to set up all these type of transitions, means that we are going to find a unitary transformation which drives these matrix elements to zero. Okay, my time is running out, but the last piece which I wanted to set up is this V of n. And then we need to set up the sum of a PQ RS and P of Q of F, no, of a V. And then we have RS anti-symmetrized. And this is multiplied with phi 0. And then I have AP, AQ, AS, AR. And then I have this AA and AI acting on phi 0. Now, if you now use Wick's generalized theorem and the contraction rules for particle and Hall states, what should this become? And now you can reason physically again, as we did before. This can at most create a one particle, one Hall state. And now when I'm acting here, I could create a one particle, one Hall state. But if you look at the contractions, so you could take a contraction here, that's fully possible. And I could take that one, but then I would always have to do some contractions within the operator. And that has to be zero, because that's normal ordered. So this one is actually zero. So the only term which survives is the term which you see here. And that's going to play an important role when we are going to analyze mathematically what Hartree-Fock theory means. So just keep that in mind. So tomorrow we are going to look also at a diagrammatical representation of these type of contractions. And the relevant material is covered by chapters 3 and 4 of that textbook by Shavit and Bach.